Well, hello, and welcome back to Risk Management. Today's lecture is picking up where the last short lecture left off, talking about probability, and specifically about why we can't assign probabilities to uncertainties. At the end of last class, I talked about probabilistic causation, and the first element of that was something that is sort of intuitive to a lot of us and seems right on the surface, but I hope by the end of today's lecture you will see to be incorrect. Here's how the statement goes. It says that every risk or uncertainty may carry a positive probability, however small, of being true. Now on the surface this sounds like quite a reasonable proposition. What's the risk of alien abduction? I think most of you would be inclined to say, at a very minimum, at least very small. Very few of you, I suspect, would be willing to say 0. And yet, by the end of today's lecture, I hope that you will understand that a good answer, in fact, probably the valid answer, is 0. Now you say, wait a minute, are you ruling out entirely the possibility of alien invasion? No, I'm not. It's an uncertainty, and maybe it's true, but we don't know that. What I am telling you is that the probability, at least according to math theory, is 0 until further notice. That's what I want to leave you with at the end of today's lecture. Let's see how we get there. What we're basically asking is this red part of this statement, or uncertainty, being a positive probability, is that true? Because we know risks can carry positive probabilities. That's why they're risks, after all. They are known to occur, and they have some probability of happening. The question is, can uncertainties have a positive probability before they're known to occur? That is, before they're risks. Let's get started. To answer this question, we first need to think a little bit about what is a probability. Probabilities come in many different forms, but we talk about probabilities of events happening. The probability of snow tomorrow is 95%. We talk about lifetime probabilities, things like dying of cancer over a lifetime, your risk is 25%. Or we can talk about it in a frequency sense, saying the lifetime probability of a groundlings being killed by an airplane crash, that is a person who's walking by as a pedestrian, is 4.2 per 1 million pedestrians. All of probability theory, really all of it, and all the statistics you're aware of, and some of you may have statistical backgrounds or finance backgrounds or economics backgrounds where you've dealt with a variety of the tests I've just put up on the screen. You don't need to know all these things. I'm just giving you examples of various statistical tests. The nice thing about mathematics is it starts from a few suppositional principles, that is, assumptions that we take to be true. And from there we can deductively build out a whole series of knowledge statements based on around those few what we call axioms. And it turns out that all of probability theory and all the statistics that you get taught in your classes really comes from just 3 of these assumptions or axioms. They're called Kolmogorov's axioms of probability. Kolmogorov wrote these in 1933, and you say to me at this point, I know some of you are thinking, wait, this is a risk management class. Why am I talking about math principles and so forth? What's an axiom? Why am I doing this? Hold on, we'll get there, because it all comes back to our intuition about risk and probability. So an axiom, as I said, is an assumption, something we take to be granted. We can't prove it to be true, we just assume it to be true. And it turns out that all of mathematics is built around certain fundamental axioms, and the same goes for probability theory. The guy who invented this, Andrei Kolmogorov, was a Russian who in 1933 came up with his axioms. He's considered the Mozart of probability theory, really a genius beyond his time. He talked about it and said 3 different things, and I'm going to translate these to English for you from the math speak that he used. The first one of these is pretty intuitive. It says that no probability can be negative, well that makes sense, and no probability can be bigger than 1. And that includes any combination of probabilities. So you can't add probabilities together and come up with something more than 100% likely, nor can you have something that's negative 10% likely to occur. Makes sense. Number 2, any outcome that can or will occur as a probabilistic outcome must be included in the set of events that you are assigning probabilities to. Okay, this one's a little harder to understand, and we're going to come back to it. It's going to be the topic of our discussion today. We call that set of events an omega. It's a Greek letter. It's just a fancy way of saying a set of possible outcomes. And we're going to talk about this number 2. Number 3 is pretty intuitive. To get the combined probability of separate events that occur, you just add their individual probabilities together. For example, if I'm flipping a coin and I can get heads half the time and tails half the time, well, then it's a 50-50 chance for either one. If I add the two together, then it's 100% likely that I'll either get heads or tails. So that's what he means when he says you combine probabilities. Just add them together. But they in no circumstances can add up to be more than 1. And that's an important point. That's the first axiom he's talking about. Okay, so on the last slide I had this sort of circle diagram there that I didn't mention to you, but I'm going to blow it up here in this slide and make this a little more explanatory. And this is going to that second axiom talking about the sample space or the set of events, or in other words, omega. That's that fancy Greek letter at the top of the page there. Imagine that all of these little circle aqua dots in the middle of this big space are all the possible events that can occur when I cause something to happen. And that this is describing everything that goes on. And then there's one little other event that possibly could occur. Either it's known to occur sometimes, or maybe it's not known to occur, but we think it might be able to occur. Where should we include this? Should we include this event in the set of events or outside? Well, if it is possible that it can occur, then really we want to include it in the set of possible outcomes. Otherwise, we're not really taking into account everything that can happen. So when we ask, for example, is this circle that I've drawn here omega? The answer would be no, because it doesn't contain one of the possible outcomes, the red dot. We would want to redraw this circle and include the red dot in the circle. If we had this, and this is all the possible outcomes, both the blue dots and the one red dot, then we would say, is this circle omega? Yes, this is omega because it contains all the possible events that can occur. Okay, this gets a little abstract, and sometimes when we're drawing circles and things like that, we need to put some teeth to it and understand exactly what's happening. So let's do this in the real world and pretend like we have a real world circumstance. Let's take a quarter, and we're flipping a quarter. Obviously, for a fair coin, the omega would include two things, either heads or tails. If we didn't have a fair coin and the coin had heads on both sides or could never land on tails, then omega would just be heads. But in this case, if it's a fair coin, heads and tails are the two possible outcomes for the coin, and so that's omega, heads and tails. But we could have a loaded coin, as I just mentioned, and omega could just be heads. But what if I had the following happen? What if I had heads, tails, or sometimes when I flip that coin, there's possibility that it might land on its edge. Now that's extremely unlikely. In fact, I've never seen that happen in my own life. I don't know if it can occur. It might even be an uncertainty. But at least we can imagine that circumstance happening in some sort of world. And so maybe we could have an omega that has heads, tails, and edge. Or let's get really crazy about it. Let's say it's heads, tails, edge. In some cases, the coin vanishes, and in other circumstances, maybe it turns into Paris Hilton. That's a pretty weird coin. But if we include all of those possibilities in the omega set, we obviously have a different contemplation about what's going on than just the normal fair coin that we all think about with heads and tails. So let's take this last circumstance here where we have heads, tails, edge vanished and became Paris Hilton. Could we include all events like that in omega and give each one of those a positive probability? For example, landing on its edge. Should we give that a positive probability, even if it's a small one, of happening? I mean, maybe it's possible the coin could turn into Paris Hilton. I don't know. It seems like it defies the laws of nature to me, but is it really an impossibility? Or could the coin just vanish, atomize, and evaporate? Quantum physics occur to the coin, and it just disappear from reality and go into a black wormhole or something like that. I suppose that's at least possible. I don't know if that defies the laws of physics or not. But could we give that a positive probability that a coin vanishes? The problem is, if we do give all of those things a positive probability, the total probability would add up to be more than 1, because some of those things probably will not occur. In fact, they are known not to occur. And so by awarding positive probabilities to impossibilities, we are in fact going to exceed the number 1 or the percentage 100 when it comes to the likelihood of all of this occurring, and that violates one of those assumptions that Kolmogorov gave us. It means it doesn't work. So the first one is no good. The second circumstance is, could we say, all right, we're not going to give weight to every possible event we can come up with in our minds that we could put in the omega, but we're going to pick some of them out, things that we think are more likely to possibly be able to occur, even if we don't know they can occur. For example, when we flip coins, if an alien were to abduct the coin in some circumstances, should we give that a positive weight even if it's an uncertainty? This is problematic, and this goes exactly back to our very first lecture when we talked about the Drake equation. It's subjective. It's in the eyes of the beholder how much weight, and if any weight should be given to any particular uncertainty. There's an infinite number of uncertainties out there, conjectures, hypotheses that people come up with. But we don't know which uncertainties will occur, and by assigning positive probabilities to some uncertainties, which may end up being wrong and be impossible at the end of the day, you're affecting other probabilities, including those of known events. And we'll come back to this point in just a moment. Our third option would be to say, let's only give positive probabilities to all known events, that is, real possible outcomes that are known. And this, it turns out, is the best option because it complies with the 3 axioms of Kolmogorov for probability theory. Although the probability scale doesn't capture all possible events when we do this, because it turns out that a lot of these may be uncertainties, it captures all known events. It's therefore objective. We're not going to subjectively talk. We can all recognize that these events are known to occur. And it always allows all known events to have a positive probability. So the best answer, if we really are following math theory, is to say that only by giving positive probabilities to all known events are we going to, in fact, be able to comply with the 3 axioms. Here's it said in a different way, if that's not helpful how I've just described it. This is Mario Bunge, an expert on causation philosophy, and he writes, far from yielding completely indeterminate, arbitrary, lawless results, coin throwing yields just heads and tails. And this, moreover, in accordance with the definite statistical law stating that in the long run, the number of heads will nearly equal that of tails if the coin is well balanced. Whereas if tossing a coin produced at times heads, and other times elephants, newspapers, dreams, or any other objects in an arbitrary, lawless way, with no connection at all with the antecedent conditions, it would be an indeterminate process. Either we would have subjective probabilities, and we would be talking right past each other in terms of what sort of probability to assign to a particular outcome, or we would violate all the Kolmogorov axioms. Let's say this in one third way if those 2 examples have not been helpful. Let's take flipping a fair coin and give it a visual space here. Here's our omega set, and these are all the set of possible events that can occur. I've also given you a probability scale here on the right side of the page, going from 0% likelihood up to 100% likelihood. And then here we can add to our space of omegas a whole bunch of different possible outcomes. Heads, tails, lands on its balanced edge, turns into Paris Hilton, or the coin is abducted by an alien before it can land. And then we ask ourselves, well, how should we award probabilities to each of these different possible outcomes? Turns into Paris Hilton seems like an impossibility. We might want to say that that's 0. But what about the alien abduction? Should we give that a small positive probability? Because it is an uncertainty that that could occur. Well, if we did that, by doing that, we would have to change the probability that it would land heads or tails. Normally, we would assign either of those events a half likelihood of occurring, 0.5 or 50% likelihood. But by giving a positive weight to landing on its edge, or by being abducted by an alien, we would necessarily have to reduce the likelihood that it would land heads or tails. And that itself would cause problems for us. So when we take that idea and we go back to what's the probability of a Martian abduction occurring, that question we asked way back on day one in this class, I'm going to make a provocative statement now that might seem a little puzzling, but in line with what we've just lectured about, and go back and listen to this again if it didn't make sense the first time. I'm going to suggest that this probability is 0. There is 0% likelihood of being abducted by a Martian. Now I know what some of you are thinking. You're thinking, wait a minute, I can't believe that being abducted by an alien has a 0% probability. Even for those of you who don't necessarily believe that there are Martians, you say, surely you have to leave a little probability of that's happening. The problem is, if you give things like that a positive probability, it will either make your probability subjective in the sense that what you include in your omega is not what someone else would include in their omega, and you're going to be talking right past each other, or you're going to violate Kolmogorov's axioms, which will have an implication we'll talk about in a minute. So the take-home point I want to leave you with is the probability of any uncertainty is not what Judge Posner said a few classes back, somewhere between 0 and 1. The answer is, it's 0. Now note what I'm not saying by this. I'm not saying that this means that uncertainties can't happen. I'm not saying that Martians couldn't show up tomorrow. The uncertainty could still be included in our omega space as a possible outcome. The fact that the probability of any uncertainty equals 0 is because of probability theory, and it's because probability theory is incapable of non-subjectively predicting uncertainties in advance of their occurrence. If tomorrow an alien showed up and kidnapped the coin, we would readjust our probabilities to take that into account. But if you don't allow for that to happen, then you're going to be stuck with either subjective probabilities or violations of the mathematical laws. Said in a different way, Johannes von Kreis, that philosopher we referred to in an earlier class, said, "It's misleading to speak of probabilities for which the underlying possibility is not known. To resolve it possibly in any other fashion, or worse, to ignore it, would make probabilities appear to reflect causal knowledge when in fact they might not." To say it differently, to say a risk exists, we establish what? Causation before we quantify a probability. We suspend our understanding of probability until we've established causation. Uncertainties have not had causation established yet. So the best we can do for them is to say that they have a 0 probability pending the outcome of better known causation. If you haven't proven causation, no matter how good you feel about the probability you are attaching to the thing that you are discussing, you are talking subjectively about an uncertainty. This has implications when we're talking about reality. So for example, there's something called hypothesis testing. Some of you who have statistical backgrounds may have heard of this. It's how we tell when we do a real test in a real world whether a coin, for example, is loaded or not. We could flip a coin 250 times, as these scientists in 2002 did, and they got 139 heads and 111 tails. They concluded using statistical testing that the coin was still fair, even though it seemed like it was pretty far off from 125 and 125, which is what you might expect if this were absolutely a fair coin. Statistically, this was within the realm of chance that the heads could come up 139 times, even though we might expect it to only come up 125 in a perfectly ideal world. But if we allowed for uncertainties in our omega set, for example, that the coin vanishes sometimes, well, maybe in the 250 tosses, it never vanished. But if we were to say, well, we're still going to give that a non-zero probability that the coin could vanish, then the hypothesis testing could mislead us about whether the coin is fair or not. In other words, if we start giving uncertainties real probabilities, it messes up most of the statistics that we use. What's the take-home point from today? Uncertainties may be true. They may end up well occurring, or they will occur in the universe we actually inhabit. But because these uncertainties are not yet causally known, we cannot assign a positive probability to any of them if we wish to make objective use of probability theory and statistics to assess outcomes for risk. That's the major point for today. So, going back to our probabilistic causation, the intuitions that we all have, the first one is the one we've evaluated today. We've said, is it true that every risk or uncertainty, and that's the key part of this phrase, may carry a positive probability, however small, of being true. For risks, the answer is yes, but for uncertainties, the answer is no, and that's what we've shown today. So we cross this one out. We say that Kolmogorov's axioms do not allow us to give uncertainties anything other than a zero probability until they are known risks. What we're going to discuss in the next class is the second component of this, namely, is it the case that when we do have an event that occurs, that its probability is determined by the amount of discoverable evidence in support of or against it? And this enters the realm of causation. We're going to leave the realm of probability behind and start to talk about evidence. And this is very important for the future parts of the class. I hope you've enjoyed today's lecture. I'm sure there's going to be great discussion on the chat boards and controversy about what we've talked about today. And I think it would be good to take this up with your classmates and see what they think about this non-intuitive result. Have a good time. I'll see you on the boards, and I'll see you at the next class.